So yeah, my talk essentially follows what Alexei presented in the first talk of this session. So allow me to acknowledge for him and Sergey, the director, one of the organizer, and also Igor and Mitun, who participated into this work, although they also moved out from PCS. Now, to start, I would like to overview more or less the mentality, the mindset that drove our research. And essentially was to use this property, this inherent property of fine tuning in flatband models. Namely, in general, fine tuning is you can define as the process in which parameters are adjusted in order to obtain certain phenomena or somehow to fit certain observations. And to use this property of fine tuning in order, for example, to study perturbation. In this case, for us, interaction. So no disorder, only interaction. So just a few words about flatband. So the core features that I think are just enough to mention is the fact that in the band structure, because we are talking about translationally invariant lattices, in the band structure, at least one band is flat, and the associated eigenstates are strictly compact. Namely, they are strictly zero almost everywhere up to few sides. Now here we see a couple of notable 1D chains. This is two-band problem over here, three-band problem, another three-band problem, and they can all be represented, for example, with this type-bending Hamiltonian, where now psi is a complex number, is a complex vector of a certain number of entries, which are the same number of bands that you have in a model. And the two important components in these equations are the matrix H0 and the matrix H1. They are both square matrices, and they encode the geometry, the profile of the lattice that we are after. Now, essentially, however, in this talk, I will focus on one of the cases that Alexei presented, which is all band flat, which essentially are a translational invariant network where all bands are flat. Now, however, they may sound very exotic and quite meaningless experimentally because it sounds quite hard to flat all bands simultaneously. However, this is one of the archetypical case, which is a very simple rhombic lattice. All opening are equal, and then you fine-tune a magnetic field in every one of these plaquettes. And at a very specific flux value, gamma equal pi, such as that the only complex number here becomes -1, so same opening strength up to the phase difference. And all bands are flat, and all eigenstates are strictly compact, and they are represented over here. Therefore, what you end up having in this system is that the dynamic of a single site excitation of or for example, a single particle is strictly confined over a final portion of the system. So if a particle, say, start here, it won't spread beyond these 8 sites. So this is what this phenomenon also goes by the name of caging. And essentially, our interest when we started to think about how interaction impact this kind of caging also was bonded with these two parallel papers that came out around the middle of 2019. And they both reported analogous results where they numerically studied the impact of kernel linearity. And they reported that, surprisingly, this caging, this single particle caging, is robust against nonlinearity. And it's not robust only in the sense of perturbative robustness, but is robust for any nonlinear strength. And therefore, we decided to have a go with this system. In particular, knowing what what Alexei was introducing before, namely that at least in 1D, although this can be expanded, maybe not for every single model in a higher dimension, that if we strict, for example, for 1D chains, 1D cases, for any number of bands, and as long as the hopping range is finite, every band can be fully decoupled or detangled. Now, what does it mean? Let me just try to show with the simplest example, because all the other cases for more bands, they are just algebraically more cumbersome, but the sort of the mind setting is the very same. And if you take a two-band problem, like sketched right here, you can apply a local unitary transformation just in one of the unit cell and then repeatedly in all the other ones. That is basically essentially just a 2x2 unitary matrix. And you are drastically simplifying the lattice from this all crisscross hopping into a decoupled dimer. So essentially, just by locally applying unitary transformations, very simple ones, as a matter of fact, you can have an analogous description, an equivalent description of your lattice, in this very case, decoupled dimers. And then if you go further on, you can also further diagonalize the dimers and therefore come up with all disconnected sides. Now you may think, okay, very good, Carlo, this is very obvious because you tell me that you can take a linear system and you can diagonalize it. And in some sense, that's true, but what is this recipe granting you is the fact that you can diagonalize it with very simple and analytically explicit expressions. Therefore, especially this first step is the core one, where you can sort of dimerize your chain through 2x2 matrices, where the only entries that you have to mind is this complex number Z1 and omega1. So therefore, we wanted to apply this knowledge in terms of studying interaction. So this is now the same two-band problem where you see appearing these red circles, which sort of cartoonishly represent the presence of local kernel linearity. And once you follow the same path to apply this local unitary transformation, you see that what is local in terms of nonlinearity now becomes non-local, namely that you are taking a local nonlinearity and make it at the very end some cumbersome non-local, non-linear network. It sounds very, very hard to deal with, and as a matter of fact, the generic expression of this is just represented over here with this Hamiltonian with a lot of terms and a lot of prefactors, which sounds like a big headache, but it actually isn't, because these terms can be actually quite governed by just the starting parameters. And what it turns out is that you can look at these terms and you can say, okay, good, you may be a lot, you may be complicated, but I can distinguish quite easily which one is going to induce me nonlinear transport and which one they are instead harmless. And then by just simply separating these two, I can ask myself, is there a way that by choosing properly these two numbers, Z1 and omega1, and these other pairs of numbers, Z2 and omega2, I can kill the terms that is going to induce me transport? And the answer is, yes, we can. For example, in this two-band problem by simply imposing this condition. So basically, we are doing a fine-tuning. We are choosing all the representations, such as Z1 in absolute value squared is equal to omega1 in absolute value squared. Now, if probably this was a lot of details, I will show an example where numerically we confirm that. We took two sample cases of this lattice. We chose one. This is what is called also Kreutz ladder, which is also experimentally realizable. It's just a crisscross ladder with all hopping equal to 1 and applying another fine-tuned magnetic field. And this is a case that the system obeys to such fine-tuning condition written over here. Instead, this one is another all-band flat Hamiltonian, where the parametrization numbers Z1 and omega1 do not obey to this fine-tuning condition. We take these systems, we add nonlinear kernel linearity with a certain nonlinear strength equal to 1. We excite a few neighboring sites, all 0 up to 3 unit cells, neighboring 1. And then we show here the time evolution. Namely, here this is propagation, and this is space coordinate, n. And in color code, we see the density. And in this case, obeying to the fine-tuning, we see that essentially all this is strictly 0, no tail, no exponentially small number, just the excitation strictly remain confined over the initially excited unit cell. Instead, those one that is non-fine-tuned, we have some spreading. We had a look as a curiosity what kind of spreading we have. So therefore, for different nonlinear strengths, we essentially measure the spreading of this process, and what it seemed to appear is some form, or at least for these orders of magnitude, some kind of subdiffusive process. Here we are measuring the second moment of this wave packet as function of the propagation time. While instead here you see these curves that are fluctuating, but they remain constant around more or less unity. which is the case that corresponds to this case dynamic. Therefore, here we have an answer, or at least one of the possible answers to the problem that was started to study in 2019 by the other groups, that not all all-band flat Hamiltonian survive caging, nonlinear caging, better to say, but only fine-tuned ones. So you need to take the family of all-band flat Hamiltonian and find those who can sustain nonlinear caging. Otherwise, in general, you will lose it because it's much harder, because you have to sustain to satisfy a specific condition rather than choosing randomly one of these two parameters and then obtain a model that supports nonlinear caging. Now, in the spirit of to test and try, similar to the spirit of also this conference, we decided to go to breach out from nonlinear regime and to try to test what is happening with quantum particles. Also because there were also some other people that were studying what is happening in with interacting particles in all-band flat cases. So we decided to start simple. We decided to go with replacing the kernel linearity with Hubbard interaction. So to take a sample and then generalize arbitrarily, but starting with sample all-band flat lattices and add Hubbard interaction. And even in this framework, we decided to start simple. So instead of going straight towards many-body problems, we decided to start with two interacting bosons. So just because if we can understand what is happening with two interacting bosons, then we probably have a clue. We can have a clue what is going on when you go to finite densities. And this is essentially, this part of the slide is what you have seen before. I just added this extra column, which is the same systems shown here for the fine-tuned and the non-fine-tuned. This is the nonlinear dynamics. So we see nonlinear caging, breaking of nonlinear caging, and here we see the dynamic of two interacting particles that are starting at the same unit cell. And in this case, okay, fine, we know nonlinear caging, and also the particles spread ballistically very quickly. Instead, in this fine-tuned case, we see that, yes, the particle spreads, the two particle spread. We see some tails that appear to propagate ballistically. However, we see also some vestiges, some kind of remaining memory that is sticking here, which is something that made us think, so we break a caging, but something is sticking over there. And therefore, in order to explain this numerical result, we went back to where we started from, to our good old detangling. And here we found that between the classical and the quantum cases, there's this term. So we take the Hubbard interaction in the original representation, again represented with red circles. We start to do the detangling. So we basically rewrite this Hubbard interaction written over here now in terms of this rotated coordinate called P and F. And we see that there is this term, which when these P and Fs were densities, so namely this where the P was the complex number representing the dynamic of this site, and F was the complex number representing the dynamic of this site, this term was harmless to ignite nonlinear spreading. So this term was not a dangerous one. We didn't need to cancel it. However, when it comes to being operator, this is a term that essentially what does it do? It erases annihilates two particles sitting in one of the dimer and recreates two particles sitting in the neighboring dimer. And therefore, since the system is translationally invariant, this term makes jump two particles from a dimer to this one, and then likewise to this dimer to the next one. And so this term is the responsible, the guilty one that is breaking caging. And this essentially allowing the two particles to escape the trap. So what does this do? This confirms the fact that we have this, that we have this departing tails, this ballistically departing tails. However, why is this excitation still being stuck here? Well, the reason is essentially that when you look at the dimers, we said that this term, which is the only guilty one for breaking the caging, it has to apply to two particles that are simultaneously sitting in one of these dimers. However, if you happen, and you can construct exact state like that you have one particle sitting in one dimer and one particle sitting in the neighboring dimer, This term is clearly useless because it requires two particles to sit in the same site. However, there are all these remaining terms that are sitting over here that are now not written because otherwise they would take most of the slide to be written, all of them. However, that are making these two particles interact. And what this corresponds is that in this system, for two-particle problem, you can construct exact eigenstates of two particles, one sitting in one state here, one sitting in the neighboring dimer here, that they form exact caged eigenstate of the system. So as often it may happen in research, as often it may happen maybe in life also, you start to look for something like quantum caging and you don't find it, you find something else. You find that you can find systems with Hubbard interacting bosons, for example, where you can construct exact eigenstates of two particles. So you end up generalizing the concept of single particle compact localized state into two particles compact localized state. And these are exact states. They exist and they are degenerate because you can construct in these two unit cell. The system is translationally invariant, so you can copy and paste in all the other remaining part of the lattice. So you don't have one of them, you have a large number of them. And just to make a comparison, although I don't want to go into the details because I'm not so confident, this kind of state, they also go called also as many body scars. Now, I call them like that also because this construction is not confined to two particles. You can repeat this scheme, this construction scheme for like 3 particles, 4 particles, and you can go on until finite filling. And therefore, you end up with a system that supports all these exact compact states of interacting particles. So we were quite surprised and pleased with these results. However, we were still remaining left with this question, what about quantum caging? Because we understood that all band flat Hamiltonian plus Hubbard interaction, that was a no-go direction. We couldn't go in that direction. So in that sense, fine-tuning was not enough when we selected Hubbard interaction. However, we thought, okay, but we can also change that. I mean, we are not sort of forced to just focus on this Hubbard interaction. So we decided to have a go and alter that. So we don't only fine-tune the underlying lattice, but we also try to fine-tune the interactions themselves. And therefore, we started simple. We started to say, good, this is again the same example. We take the Hubbard interaction written again here, Hubbard interaction term on the upper side, Hubbard interaction term in the lower side. And then we add this extra term, which is particle number in here and multiplied by the particle number down here, multiplied by a prefactor 2, which is essentially adding basically an interaction between two particles sitting in this unit cell. Now, why is this one special? Because you can take this interaction and do a little bit of simple algebra, and you can write it down equally as this product. This is just the particle number operator in one of unit cell. This one is the same thing, just with this prefactor -1. Now, why is this doing the job? Well, you can say that because if you take this rotation, so if you do the detangling through this generic unitary transformation and you try to rotate this one, this interaction is self-similar under this transformation, namely that you end up with the same product of the particle numbers operator. Therefore, when you go into this dimerized representation and you have the interaction that is interacting two neighboring dimers, this interaction right here, it counts how many particles is here, how many particles is here, but it's not making any jump. Therefore, particles that are sitting in one dimer remain there, particles that are sitting in this dimer remain here, and this repeats for all neighboring dimers. Therefore, in the original representation, particles that are starting in a certain portion of the system, they will not travel. And therefore, this interaction is completely killing any charge transport. And notice that I never had to speak at all about the interaction strength. So this is not a perturbative effect. This is something that can be for very small prefactor in front of the U1 in the total Hamiltonian, or for very large one, or just for make it one, just to don't bother even to talk about. Now, last comment that one may think is, okay, very good, Carlo. Thank you very much for telling us that this interaction works, but it doesn't look like something that we can achieve experimentally, or this doesn't look like even that it makes sense. And probably we can agree with that. So, but you can construct more. For example, if you stay in the same lattice, another interaction is this one. Again, product of particle number operators. So when they are self-similar, when you try to do local unitary transformation inside of the unit cell. However, if you try to sort of open up this product, you see that the first term is a particle number operator here multiplied by particle number operator in the same chain in the next unit cell, which basically consists in this arrow right here. And all the remaining free terms are the remaining free arrows that are sort of appearing over here. So basically, what you are constructing is a nearest neighbor interaction that essentially follows all the hopping terms of this lattice. And this one is also not inducing any transport. So you can look at this chain with this interaction as a sort of, through the Jordan-Wigner transformation, as a sort of a spin chain with this profile, which is living on a chain with this crisscross hopping with a certain fine-tuned magnetic field. And this is a chain that basically the charge transport is completely killed. So in this system, there is absolutely no charge transport for any interaction strength. And I would like to sort of summary up this by listing the properties that basically we have found, because this is just this talk was essentially focused on this two-band problem, but the same results can be obtained with just a little bit of patience to deal with the algebraic details, but essentially it's the same thing, just with more terms. When you go for any number of bands, when you raise the dimensionality from one dimension to higher dimension, and essentially, as I said, that there were no really assumption to the type of many-body statistics. And by this construction, you can also prove that this system possesses an extensive number of local integrals of motion. And they are local because they essentially span over these four sides. And they are even simple to be computed. I didn't report here the exact expression, because if you see that essentially the particle number the number of particles that is sitting in this dimer is conserved, you take the particle number, namely the particle number term here plus the number of particle term here, you rotate it through your unitary transformation, and you get the expression of it. So you have even the analytical expression of these local integrals of motion, and they are really local, they are compact, not no exponential tail. And since I have 1 minute left, I would like to comment on a result that I didn't include. Here is that we also study what happens with the heat transport instead of only charge transport, and we saw that essentially in this case also heat transport is completely killed. If you have low density of particle, it is killed by default. If you have like half filling in this two-band problem, you potentially have heat transport, which is exponentially killed over growing length of the system. So essentially, this system is also not supporting, or it has an exponentially decaying heat transport. And with that, I would like to essentially conclude the talk by saying that these are the take-home messages. That, the overall message is fine-tuning allowed to tame perturbation. For example, in this case, interaction, but other ones can be like disorder, driving, external field. These are all terms that you can say something. And then that we studied the impact of nonlinearity and Hubbard interaction, and then fine-tuning certain interactions in order to obtain some strict localization of charged particle. And as I mentioned, I just would like to say that we also try to do the same tricks, just when we are not in the all-band flat case, but when we have a mix of flatbands and dispersive bands, and you can repeat the whole construction and end up having what in the community now is called the disorder-free localization. And with that, I thank you for your attention.
Thanks, Carlo. So is there any question from the audience? Then I may ask a question. So in your anybody interaction in quantum version, so what is the really condition that this interaction become invariant under this unitary transformation?
For us, it may be not the only one, but for us, what we found is that if we are able to write in terms of combination, what is that? Yeah, like this one. If we are able to write it in terms of sum of particle number that is within one of the number of particles within the unit cell, then when we do the rotation, this sum is preserved. So it may be not the only one. There can be more complicated one, but we liked this one because when you talk about particle number, this is something that has some connection with reality. You can have other maybe more contorted ones that mean nothing, but they still work.
Yeah, so I would like to know about some generalization of this because this is a one specific case. So
I just decided to follow this because it's the one that is the least cumbersome example.
Okay.
I mean, we can repeat the same trick with this free band problem that I mentioned in the beginning, this rhombic lattice with magnetic field. And you can go on with as many number of bands as it pleases you.
Oh, okay.
And with some patients, you can go also in 2D. And we constructed some model that support this kind of absence of charge and heat transport in 2D. Just that they didn't fit the talk.
Okay.
Yeah.
We have a question? Yeah.
Thank you for the nice talk. Maybe I must misunderstood. You mentioned that this interaction is maybe hard to get, but it seems like if you had like a quantum spin system and the rungs of your system would be spin states with an SUN symmetry, you get it for free, wouldn't you?
So you mean that so I was meaning that the previous one?
Yeah. That is total n minus 1 times total n. So if you have an SUN spin system, that's exactly what you get, right?
So because sometimes it sounded like that you have this on-site terms and then this interaction between these two. I mean, I'm not saying that it doesn't have it, just that this prefactor 2 sounded a little bit fishy, so that the interaction between particles that are sitting here is twice the interaction that on the on-site. This was sometimes raising a bit of eyebrows. So I thought, well, maybe this one is not so easy experimentally to try to achieve it because of this prefactor 2. So this one instead with all prefactor equal to 1 sounded...
But the lower line is n times n minus 1, right? That's what you get.
Yeah.
Yeah, that you get it for free.
Yeah. So for me, that very good. Yeah.
I have also another question, Carlo. So
right.
In the case of this nonlinear caging, so you can get the single particle flatband if you linearize your system, I guess, right? So that's why this caging works very well.
Well, it doesn't work very well everywhere. So, I mean, you can probably do this linearization also in the non-fine-tuned case, and then it won't work.
Yeah, so it seems like this unitary depends on this fixed point of a nonlinear equation. So whenever we have different fixed point, do we have a different unitary transformation, or?
I'm not sure if I grasped what you meant. So, no, probably you may repeat the question.
Okay, then probably we can discuss later. Any other questions? Okay, if not, then thanks again for Carlo for interesting talk, and we will end our this session. Thank you very much.